Section 3.6 again, position, velocity, and acceleration of a moving object. Take a review about what we learned in the last class. Review number 1, the formula to compute the average velocity of a moving object on a time interval from t1 to t2 is the position of the object at the time t2 minus the position of the object at the time t1 over t2 minus t1. Review number 2. Fact number 1. Derivative of a function at a point A is the slope of the tangent line to the graph of the function at the point P. The point P, x coordinate is A, y coordinate is function value at A. This point is on the graph of the function. Review number 3. Fact number 2. If s of t is the position function of a moving object, then the derivative of the position function at A is the instantaneous velocity of the object at the time A. Review number 4. Fact number 3. Plot the graph of the position function, then the slope of a tangent line is an instantaneous velocity. Suppose this curve is the graph of the position function. This is a tangent line to the graph. By fact number 1, the slope of the tangent line is derivative of the function at the point A. Because the function now is a position function. By fact number 2, derivative on position function at the point A is instantaneous velocity at A. Therefore, slope of a tangent line is instantaneous velocity at the time A. Review number 5. Fact number 4. Plot the graph of the position function. Then the slope of a secant line is an average velocity. Suppose this curve is the graph of the position function, and this line is a secant line. Suppose the secant line intersects the graph of the position function at these 2 points. Then by the slope formula, the slope of this secant line is y2 minus y1 over x2 minus x1. Now, S is position function of a moving object. So, S of B, this is the position of the object at the time B, minus the position of the object at the time A, then over B minus A time elapsed. So this is the average velocity of the object on the time interval from A to B. Now, example 1. A state patrol station is located on a straight north-south freeway. This is the freeway, and this is the patrol station. A patrol car leaves the station at 9 a.m. heading north with position function S of t that gives its location in miles t hours after 9 a.m. This is the position function. It is the distance between the station and the car. The graph of the position function is shown in this diagram. In this diagram, time is 0 corresponds to 9 a.m. Time is 0.5 corresponds to 9:30 a.m. Time is 1 is 10 a.m. Assume that as the position is positive when the car is north of the patrol station. From this diagram, when time is between 0 and 2, the position function is positive. That means that between 0 and 2, the car is north of the station. Between 2 and 3, the position function is S is negative. That means that between 2 and 3, the car is south of the station. Part A. Determine the average velocity of the car during the first 45 minutes of the trip. 45 minutes is 0.75 hour. By formula, the average velocity of the car on this time interval is the position of the car at 0.75 minus the position of the car at 0 over 0.75 minus 0. From the diagram, when time is 0.75, 0.75 is here. The height of the graph is 30. So therefore, the location of the car at 0.75 is 30 miles north of the station. The position of the car when time is 0 is 0. So the average velocity is 40 miles per hour. Part B, find the average velocity of the car over this time interval. Is the average velocity a good estimate of the velocity at 9:30 a.m.? Part B has two questions. To answer the first question, by formula, the average velocity over this time interval is position of the car at the right end point minus position of the car at the left end point. When time is 0.75, 0.75 is here. The height of the graph is 30. When time is 0.25, this is 0.25. The height of the graph is about 10. So the average velocity is this number. This number is 40. To answer the second question, in part B, we need to recall that an average velocity is the slope of a secant line. And an instantaneous velocity is the slope of a tangent line. This average velocity is the slope of this red line. This red line joins this point and this point on the graph. This point corresponds, time is 0.25, and this point corresponds, time is 0.75. The velocity at 9:30 a.m. 9:30 a.m. in the graph is 0.5. The velocity, this is instantaneous velocity. The velocity at 9:30 a.m. is the slope of the tangent line to the graph at 0.5. You should draw a tangent line here. And then you will see that the tangent line and the red line are almost in parallel. So their slopes are almost equal. Therefore, the conclusion, the answer to part B is the average velocity 40 is a good estimate of the velocity at 9:30 a.m. Part C. Find the average velocity of the car over this time interval. Estimate the velocity of the car at 11 a.m. and determine the direction in which the patrol car is moving. Here is the solution to part C. The average velocity of the car over this time interval is -60. This number is the slope of this red line. This red line is a secant line that joins the 2 points on the graph, corresponding to the time 1.75 and the time 2.25. The velocity of the car at 11 a.m. 11 a.m. in the diagram corresponds to time is 2. The velocity here means instantaneous velocity. The velocity of the car at 11 a.m. is the slope of the tangent line to the graph at time is 2. So at time is 2, draw a tangent line to the graph. Because the tangent line is almost parallel to this red line, the slope of the tangent line is almost equal to the slope of this red line. So we can estimate the velocity of the car at 11 a.m. by the average velocity over this time interval. So therefore, we estimated that the velocity at 11 a.m. as -60. Negative means the car is moving in the south direction at 11 a.m. The south direction is a negative direction, and the north direction is positive direction. Part D, describe the motion of the car relative to the patrol station between 9 a.m. and room. Room in the diagram corresponds to time is 3. To answer the question, we need to recall that instantaneous velocity is the slope of a tangent line. Between 0 and the time here, all the tangent lines to the graph have positive slopes. So between 0 and the time here, the car is moving north. At the time here, the velocity, because the tangent line is horizontal. So at the time here, the velocity is 0. That means that the car takes a break at the time here. Between the time here and the time here, all the tangent lines have negative slopes. So between this time and this time, the car is moving south. At the time here, the car takes a break again because tangent line here is horizontal, slope is 0. So velocity is 0. After the car takes a break at this time, the car moves north again because tangent line again has positive slope. Example 2. The graph of the function s represents the position of an object moving along a line at time t from 0 to infinity. Part A. Assume the velocity of the object is 0 when t is 0. For what other values of t is the velocity of the object 0? Recall that the slope of a tangent line is velocity. At time is 0, tangent line there is horizontal. So at time is 0, velocity is 0. The other times when the velocities are zeros are t is 1, t is 2, t is 3, because tangent lines there are horizontal. Part B. When is the object moving in the positive direction, and when is it moving in the negative direction? Between 0 and 1, all the tangent lines have positive slopes. So between 0 and 1, the object is moving in the positive direction. Similarly, the object is moving in the positive direction over the time interval from 2 to 3. Between 1 and 2, all the tangent lines have negative slopes. So between 1 and 2, the object is moving in the negative direction. Similarly, from 3 to infinity, the object is moving in the negative direction. Part C. Sketch a graph of the velocity function. Because velocity is the slope of a tangent line, so in part C, we need to sketch a graph of the slope of the tangent line to this curve. For the convenience of my presentation, let me copy this figure here. Now, I sketch the graph of the slope piece by piece. The first piece is between 0 and 1. At 0 and at 1, tangent lines there are horizontal. So at 0 and at 1, slopes are 0. Between 0 and 1, the slope of tangent line at any point is positive. So the graph of the slope between 0 and 1 looks like this curve. Suppose the slope is the largest when time is 0.5. Second piece. The second piece is between 1 and 2. At 1 and at 2, tangent lines are horizontal. So at 1 and at 2, slopes are zeros. Between 1 and 2, slopes everywhere is negative. So the graph of the slope between 1 and 2 is this curve. Suppose the slope is the smallest when time is 1.5. The third piece is between 2 and 3. At 2 and at 3, tangent lines are horizontal. So slopes there are zeros. Between 1 and 2, the slope of the tangent line everywhere is positive. So the graph of slope is this curve. And suppose the largest slope appears at time is 2.5. Now the last piece, between 3 and infinity. When time is 3, tangent line is horizontal. So at 3, slope is 0. At 3, slope is 0. When time is greater than 3, slope is negative. So the graph over the time interval from 3 to infinity is this curve. Part D. When is the object speeding up? When is it slowing down? To answer the questions, we need to recall that speed is the absolute value of velocity. Now, from 0 to 0.5, the graph of the velocity is increasing and is positive. So speed is increasing. Therefore, the object over this time interval is speeding up and is moving in the positive direction because velocity is positive. Between 1 and 1.5, the graph of the velocity is decreasing and is negative. When we take absolute value on this piece of the graph is increasing. Therefore, speed is increasing. So on this time interval, the object is speeding up and is moving in the negative direction because velocity is negative. Similarly, between 2 and 2.5, the graph of the velocity is increasing and is positive. So on this time interval, speed is increasing. So the object is speeding up and is moving in a positive direction. The interval from 3 to infinity, the graph of the velocity is decreasing and is negative. When we take absolute value on this portion of the graph, this portion is increasing. So over the time interval from 3 to infinity, the object is speeding up because the absolute value of velocity is increasing and is moving in the negative direction because velocity is negative. Now about slowing down. From 0.5 to 1, the object is slowing down because the graph of the velocity is decreasing and is positive. So speed is decreasing. Between 1.5 and 2, the graph of the velocity is increasing and is negative. When we take absolute value on this piece of the graph, this piece is decreasing. So over this time interval, speed is decreasing. Therefore, the object is slowing down and is moving in the negative direction because velocity is negative. Now, the last interval from 2.5 to 3, the graph of velocity is decreasing and is positive. So therefore, speed is decreasing. So over this time interval, the object is slowing down and is moving in a positive direction. Example 3. So in this diagram are the graphs of the position functions of two runners, A and B, who run a 100-meter race and finish in a time. Part A. Describe and compare how the runners run the race. Runner A runs at a constant speed because the graph of the position function for runner A is a 9. A 9 has constant slope. Runner B starts slow and increase his speed as he runs. This curve is the graph of the position function for runner B. At the beginning, this curve has small slope, but the slope is increasing as time is increasing. Part B. At what time is the distance between the runners the greatest? At about 8, the distance between the runners is the greatest, about 30 meters. At A, the height of the graph for B is about 30. That means that at time is A, runner B is about 30 meters from the starting point. At A, the graph for A, the height is about 60. That is, at time is A, runner A is about 60 meters from the starting point. So the distance between them is 60 minus 30 is 30 meters. Part C. At what time do they have the same velocity? At about 8.5, the runners have the same velocity. At 8.5, the tangent line to the graph of runner B has the same slope with the graph of runner A.